Welcome to video number 4 in this series. In this video, we'll be talking about significant figures, or sig figs. Sig figs tell you about the inherent certainty of a measurement. They are therefore important in a number of fields in engineering and the physical and social sciences. In fact, using the incorrect number of sig figs can have disastrous real-world results. For example, misuse of sig figs has resulted in crashing rockets, massive financial losses due to currency trading errors, and parliamentary changes. We'll be talking about the parliamentary change at the end of the video. With that, let's start talking about sig figs. In the previous video, we ended with these two balances and measurements. Each of these two measurements has both certain and uncertain values. For the high precision balance, we have 4 certain values and 1 uncertain value. The uncertain value is in the 10,000ths place. For the low precision balance, we have 1 certain and 1 uncertain value. The uncertain value is in the 10ths place. When considering a measurement, we call all the reported certain and uncertain figures significant. Therefore, the high precision balance that reported the mass of 1.7631 grams contains 5 significant figures, while the low precision balance that reported the mass of 1.8 grams contains 2 significant figures in that measurement. There are well-defined rules for determining the number of sig figs in a value. I will go through the rules first and then give several examples. The first rule is that all non-zero numbers are significant. The second rule is that all zeros in between non-zero numbers are significant. The third is that zeros at the end of numbers are significant if the number contains a decimal point. Finally, zeros that are simply placeholder digits are not significant. For the value 132, this number has 3 non-zero numbers. Therefore, it has 3 significant figures. 1,302 has 3 non-zero numbers and 1 zero in between 2 non-zero numbers. It therefore has 4 significant figures. 1,320, on the other hand, has 3 non-zero numbers and 1 zero that's a placeholder value. It therefore has 3 significant figures. 1,320.0 has 3 non-zero numbers and 2 zeros. One of those is at the end past the decimal point. It therefore has 5 significant figures. Finally, 0.0132 has 3 non-zero numbers and 2 zeros that are simply placeholders. It therefore has 3 significant figures. When writing significant figures, scientific notation can become incredibly important. This is because scientific notation can eliminate the ambiguity in the number of significant figures you have. All of the non-significant figures will become incorporated in the exponential term. For example, let's consider the number 1,320. From the rules we went through, we said that this had 3 significant figures. But what if that zero is really significant? What if our uncertainty is in that last digit? If we use scientific notation, all ambiguity becomes eliminated. If we have 1,320 and we have 3 significant figures, reporting this as 1.32 times 10 to the 3 will remove that zero. We therefore have 3 significant figures, and that's obvious in the reported value. If that zero is significant and we report 1.320 times 10 to the 3, we now know that that has 4 significant figures because that zero comes after the decimal point. Just as there are rules dictating what figures are significant, There are also rules dictating how to use them in calculations. In general, the number of significant figures you obtain in a calculation is dictated by the number of sig figs in the value with the most uncertainty. The physical basis for this rule is that you can never be more certain than you are in your least certain measurement. We will find that addition and subtraction have different rules than multiplication or division. For addition and subtraction, the result should have the same number of digits past the decimal place as the number with the least number of digits past the decimal place. As an example, let's look at the following problem. Here, we're adding together three numbers. We're adding together numbers that contain as many as 7 significant figures and numbers that contain as few as 3 significant figures. If we go through and add these together, ignoring the number of significant figures, we obtain this result, 127.9762. This contains more significant figures than we can report because the number of significant figures is equal to our most certain measurement. Instead, we have to have the number of significant figures dictated by our least certain value. In this case, we can only report 2 past the decimal place. To obtain the final result, we have to apply rounding rules. The rounding rules that we're going to use are as follows. If we have 0 to 4 in the digit just past our significant digit, we're going to round down. If we have 5 to 9, we're going to round up. Therefore, the answer that we would report would be 127.98. For multiplication and division, your answer is dictated by the total number of sig figs in the input values. Your answer should have the same number of significant figures as the input value with the least number of significant figures. As an example, let's look at the multiplication of these three numbers. We have 2 numbers that contain 4 significant figures and 1 number that contains 3 significant figures. Multiplication yields this value, which contains many more significant figures than any of our input values. The number of significant figures that we need to report will be dictated by 157, which contains 3 significant figures. Therefore, the value that we would obtain when we consider significant figures would be 622,000, or 6.22 times 10 to the 5th. With that, we've reached the end of this video on significant figures. I would say that in this video, the most important points are the rules governing how you calculate the number of significant figures and how you use those in subsequent calculations. So, all non-zero figures are significant. Zeros are only significant if 1, they're in between non-zero values, or 2, they're at the end of a number after a decimal point. If their zeros are simply placeholder values, they're not going to be significant. When doing calculations, the lowest certainty value is going to dictate how many significant figures you put in your reported value. So with addition, we look to the number of significant figures after a decimal point. For multiplication and division, we look at the number of significant figures in the various input values. In our next video, we'll be talking about dimensional analysis. So, at the beginning, I said that significant figures can alter parliamentary results. So, how did significant figures lead to a parliamentary change? Without going into the fine details of German constitutional law, Germany has the so-called 5% clause. For a political party to seat a member in the Bundestag, it needs to have garnered at least 5% of the total vote. In 1992, in the state of Schleswig-Holstein, the Green Party had 5% of the vote after all votes had been counted. This meant that the Green Party could seat a candidate. However, it left the Social Democrats, the SPD, 1 seat short of a parliamentary majority. When someone went back and looked at the vote totals, it turned out that the Greens actually had 4.97% of the vote. It was argued that 3 significant figures is probably more appropriate than 1 significant figure given the accuracy in modern vote counting. So the Greens lost a seat because they had less than 5% of the vote. The SPD ended up picking up a seat after votes were recalculated, and they ended up gaining a majority in the Bundestag.